Air pollution is not only harmful to humans, but also to animals, plants, the weather and climate. It can reduce the diversity and abundance of insects and stunt the growth of trees, making them more vulnerable to pests and diseases. Air pollution can reduce the amount of sunlight reaching the Earth's surface, but also trap more heat and warm the Earth. So mapping and interpolating air pollution is important for several reasons. First, it can help us visualize the spatial distribution and variation of air pollution across regions and countries. Second, it can help us identify the sources and causes of air pollution, such as traffic, industry, or crop burning. Also, it can help us assess the health risks and impacts of air pollution on human well-being and the environment. And finally, it can help us evaluate the effectiveness of policies and interventions to tackle air pollution and improve air quality. So in today's tutorial, you will learn how to map air pollution using ggplot2 and rayshader and R and create some beautiful and effective 2D and 3D maps of air quality index data. What's up, people? This is Milos. Welcome back to my channel as I take you on another exciting data visualization and geospatial journey with R. This time, we'll be creating air pollution maps using the World Air Quality Index data. So first of all, we'll be actually getting the data by communicating with the World Air Quality Index API. The second thing, we'll be interpolating the data based on the existing stations. And the third thing, we'll be creating pretty and effective 2D and 3D maps of air pollution. Let's kick off our adventure by first of all installing the packages that we need and then loading them into this R session. So we're going to go ahead, create this object called libs. It's going to be a list of the names of the packages that we need. And the first one is the Tidyverse umbrella package for data wrangling and data visualization. The second one is the HTTR, which we'll be using to create a GET request, send it to the AQI API, and then get the data back. The third will help us fetch the national boundaries of Bosnia and Herzegovina in the shapefile format, so that's GISCO-R. The next package is the asset package, which will help us actually modify this shapefile and also create a grid upon which we can then interpolate these values. And speaking of interpolating values, we will use here the package called gstat for the purpose. And finally, for creating breaks or bins, we'll be needing class int package. Now, the next step that we need to do here is to check if these packages are indeed installed on our system. So what we're going to do is we're going to take this list that we just created, and then we're going to go through the row names of already installed packages. All right, so exactly like this. Now, if these packages are not installed, so if any of these installed libs equal false, then we open this curly brackets and then we say basically, yeah, install.packages. So that's the way that you actually install packages in R. Now there's a trick here because we don't want any kind of packages. We want libs, and also not all the libs, only those that are not among the install libs. So once we actually install packages, the very last step is to simply load them into R, which is quite easy. What we need to do here is we simply need to apply to the list of libs, we need to apply this argument, which is called library, which in R actually loads. Okay guys, in today's tutorial we'll be mapping air quality index, and the World Air Quality Index that we'll be using here is a composite measure of how polluted the air is in different locations around the world, whether we're talking about, towns or countries or regions. And when I say it's index and when I say it's a composite measure, it means that the measure itself is based on the levels of different things such as particulate matter, ozone, nitrogen dioxide, sulfur dioxide, and also carbon monoxide. So in creating this index, the authors have created actually a scale from 0 to 500, where basically you can see here 0 to 50 is good, and then 51 to 100 is moderate, and then everything after or like above 100 is actually unhealthy for different levels. So a good thing about this measure is that it's called the World Air Quality Index for a reason. It means that it can actually be compared across different locations and countries, which is awesome for us. And here I'm actually on this page where the API is. API will allow us to communicate with this website and get the data we want. So I'm here at aqicn.org/API. And here, the first thing, as you can see, is the initial setup here on this page. And it says that the first thing you need to do is you need to get your token from the data platform token. So you don't need to register or anything. You just click here on this link, which is data-platform token. It's going to open a new page where you simply need to agree with the terms of service. So you click here, you take this one, and then here you fill out your email address and your name, and then you submit. And once you submit, this actually will give you then, this service will give you your token, which you can then use to fetch the data. So how do we fetch the data from this website? So the first thing, once you get your token, you can go to this page, which is basically on the same website, but just a different page on it, aqicn.org, and then /json-api/demo. So this is where you can try out what actually you can download. So if you actually enter your token here, you can play with the keywords on this right-hand side. So you can, for the keyword here, you can put, for example, either the name of the city or the name of the country. So if you put the name of the country, you're going to actually get all the stations that are measuring of course, the air pollution quality index, and then, of course, the date when this was measured. So this is very important. Then if you actually scroll down, you can also see some other pollutant measures, but in this tutorial, we'll be just focusing on the air quality index. So we're not going to go into these individual ones. Now here you will find some reference codes and how to actually build this. Of course, this is not really our code, so it's not that helpful, but what it helps is it actually shows you what is the URL that you need to use here. So what you need to do is you need to copy this URL. This is going to be our main URL. And then on top of that, what we're going to do is we're going to add this end keyword equals to, and then we will also gonna write the country that we're interested in. This tutorial specific will be fetching the data for Bosnia and Herzegovina, but in essence you can get for any country where the data is available. So the next thing is then to simply copy this part of this chunk of the codes, which we will then use in R. And once we actually build this request, we will send it to this API, and then we will get the data on air quality index for all the stations for Bosnia and Herzegovina. All right, we are back in R, and I hope that you copied that base URL from the website. So it's here. And the next step that I'm going to do here is, first of all, I'm going to wrap it around that. I'm going to wrap a double quotation mark. So I'm going to define it as a string, and then I'm going to pass this to URL. So I'm going to create a URL object. So now here you need to put equals to, and then finally you should insert here your own token. So it's a combination of letters and numbers, remember, that you got from the previous website. And once you do that, you should add here ends, keywords, and then keyword equals to, and then the name of the country. And here I use a shortened version of Bosnia and Herzegovina, which is also going to work for me. So once you define here the URL, the next thing is to build a request to the API that's going to be sent to the API. So the request is the following: request equals to, and here we use HTTR and the get to build the get request for the API. So simply here we pass that URL equals URL. Okay, once you inspect this request that you just built, what you will get here is the response, the dates together with the time. Status 200 means that it was successful, so it didn't throw any error. Content type, application/JSON. So this is very important in the next step when we will actually fetch the data from the content itself. Our next step is to, first of all, parse the JSON data from the response, then to map it onto a data frame, list of data frames, flatten it, and finally create a single data frame. So this involves several steps, which we will conveniently just put within a function, but I will actually show you as we go through this function, make AQI data frame. I will show you actually what each of the steps entails. So in this function, the main object that we're gonna argument that we're going to require is the request argument, which we previously built. So as I said, the first one is parsing the JSON data from the response. And this is how we do it. So we create an object here, which is going to be called WAQI_data. And then here we use HTTR to access this content. So first of all, we pass here the request that we previously built. Second, we say that we want this information parsed. Third, the type is here, of course, as we previously saw, application JSON. And importantly here, what we want to get is the data from this extract. So once we actually run this, let's just run this part. And once we run this part, let's also inspect the structure of this data that we just parsed from the JSON. So what do we actually work with here? And as you can see, it's actually very complex, very complicated. So there are lists of lists within lists. So here, the main list is something that has the unique ID of a station. Then there is AQI, so that's really good for us. But we also need the geographic coordinates. So that's where the problem starts, because you see station here, which is one of the members of the list, also has the list inside. And not only that, geo, which are actually the coordinates, is the list of 2. So this looks very, very complicated at the moment, and we want to simplify it. So the way to simplify this is, first of all, coerce this into a list of data frames, but then also flatten these data frames so that we get columns in the order we want. And this is what we're gonna do next. So we're gonna create here a flat list, and we're going to work on the previously created data. So for that, we're gonna be using per with triple R, as you can see. And first of all, we're gonna map this structure into a data frame, but that's not gonna be sufficient. We will need also to flatten those columns. So again, we'll be using per map, and then within this one, we also call per flatten argument. Okay, so once more, let's run this thing. And once we run, we also want to inspect now the structure of this newly flattened object. So I'm just going to increase here bits. And what you can see now is quite different things. So here now we got only a list of lists. So there are no sub-lists within those lists of lists. And as we can see now, what we did is we extracted those list of lists and put into this parent list, so to say. So what we have here is the unique identifier of a station. We have the AQI value, but then we also have the coordinates here, which have a bit weird name, but we're going to handle that. The most important thing is that we now have only a list of lists. So this is then quite easy, because what we can do next is we can simply use this list of lists and just convert it into a single data frame. And we can do that because the column names in those different list of lists actually have the same names. So in this step, we're going to create a new object, which is actually going to be a single data frame. And so what we're going to do here is, first of all, we're going to transpose those columns into rows. So that's the first step. And for that, we just use this argument t. Now, the next step is, because working with a list of lists, we need to dissolve this list into a single one. So for that, we use this do call. And then finally, we want to bind those rows together and build a data frame. So taking from each of the lists, we turn that into a row and then just like glue them together one below another. So for that, we need cbind. And then finally, we simply need to say here, okay, we need to apply to this previously created object. And the very last step is to coerce everything into a data frame format. So that's how it's done. All right, so we can now simply run this whole thing, and then we can also check how this looks like. So because we now created a data frame, we can perhaps simply inspect maybe the first few rows here. This is what we're going to do. And then, as you can see, we have a single data frame. This data frame has all the fields we need. From this data frame, we only need to extract the second column, which is AQI, then the 7th column, which is latitude, and the 8th column, which is longitude. And this is what we're going to do next. So we're going to simply add to this a pipe and then call dplyr select and simply say, yeah, we want columns 2, 7, and 8. So if we then run this again, and if we also then inspect this, you will see that exactly now we have AQI, we have latitude and longitude, but of course the names are not correct, so we want to also change that. That's pretty easy. We can just say here names, and then we can pass this object here, and then we can define the list of columns. So starting with AQI, and then lat, and then long. Now, of course, one more thing here, which is very important, is once we do these transformations, all these three fields, unfortunately, are going to be declared as strings, even though they are numbers. So there is one last step that we need to take and declare these as the actual numbers. So I'm just going to create this very last object, and I'm going to build a pipe here, and then I'm going to use here a dplyr option, which is called, or function, which is called mutate at, which is going to help us apply a function on multiple columns. So the columns here are exactly these columns, all of them, and simply I want to apply here as numeric. So this is going to turn all of them into numbers. And finally, once we are done with all these, we can simply return this final object since we're building a function. And then, after we built this function, here we can simply call it. So we can call it and name it in the name of this object. So we're going to call the function, which is make AQI data frame. And then very importantly here in the brackets, you need to put requests. So request, in our case, request equals request, because that's how we named it. And then also, because there are some missing values for some stations, so they did not record for that day, you simply can omit those values because we only need the proper values. So all those stations that we got are irregularly distributed across Bosnia, but in order to predict the average AQI for the entire country, we need to actually first of all organize the whole thing as a grid. So what we're going to do next is we're going to take a shapefile of Bosnia-Herzegovina, just national boundaries. Then we're going to create a grid based on its size, and it's going to be a grid of a certain size. So we're going to go for 100 square kilometers for each cell. And then finally, what we're going to do is we're going to simply intersect this grid with the national boundaries of Bosnia so that we get something that is shaped as Bosnia. So that's basically it. We did also in one of the previous tutorials cover how you can make grid maps, so you can also check that one. But now we're simply gonna reiterate that process. And we're gonna start off by first of all loading the national boundaries of Bosnia-Herzegovina. So here we call to rescue gisco r, and then gisco get countries. And then here we need to specify for the country the ISO2 code for Bosnia-Herzegovina, that's BA. And then here we also need to specify the resolution that we need. So we're going to go for the crispest resolution, which is 1. All right, so once we have this, the next thing is we need to reproject this into a metric coordinates reference system, because otherwise we won't be able to create a grid. So we're simply going to create here an object called country transformed, and then it's going to be based on this country SF. So we build here a pipe, and then from the SF package, we use the function called stTransform. And then the metric system here, so there is here 3857 that you can, for example, use. There are more, but I'd like to use this one. All right, so once we actually do that, the next step is to create the grid itself. So we're just going to call this country_grid. And again, from the SF package, there's a very convenient function that allows you to do that. It's called stMakeGrid, and also very intuitive. So here we're going to pass that we want a grid which is based on the size of this country transform object. And a very convenient thing is we can also specify here the cell size. So this is done through units, because we can specify in square meters, square kilometers, or hectares. We can specify what we want. So I'm gonna go ahead here and choose 100 square kilometers, and this is how you also define that. So it needs to be passed as a string format, and it needs to be in this form. So you can choose a lower or a higher value here, but remember, if you choose the cell size to be lower, then it's gonna involve more computation costs. It's gonna be slower. The second thing we need to define here is, what we are fetching. We're fetching polygons. And then finally, we want to return here squares. So square equals true. If you put here square equals false, it's going to give you hexagons, which we don't want at the moment. So this one is called country grid. Now, the second step is to intersect this country transformed with this country grid so that we get a country grid in the form of Bosnia-Herzegovina. So we are here just going to build, this pipe. And to intersect, we can use st intersection from the SF package. So what do we want to intersect here? Well, obviously we want to intersect with the country transformed. But that's not everything, because what happens sometimes is that this throws an error. So the way to actually deal with this is to create a very small, actually non-existent buffer, but simply to call a buffer here. So st buffer, wrap around this one, and simply define the size of the buffer 0. So this is just used to deal with certain situations where what happens is when you intersect those grids with the country polygons, grid might be actually open, and then it's not anymore, a grid or a polygon. It might turn into a line or a multi-line. So that's a problem, and this is going to mitigate that. So once we do that, we need to make sure that this is still an SF object. So we're just going to use, again, from the SF package, st as SF to declare that. And one more thing is we want for each of those rows to have specific IDs so that we can also identify them, though this step is not maybe necessary in our case. So one thing that we should also do is, again, with this intersection, as I said, maybe some polygons will change their type and turn into lines or even points. So we just want to make sure that we validate that this object is fine. So we're going to use here st make valid. And as a final step, you remember that at the very beginning, we converted this object into a metric coordinates reference system. So we're going to put it back into the standard one. So we're going to use here st transform once more, and then simply turning back into WGS84. Okay, the very, very last step here is to define the geometry field, which in the SF package or in the SF dictionary basically just means a collection of items, in our case, a collection of polygons. So we're gonna simply say here that st geometry is going to be for this country grid called geometry. If you follow all the steps and you finally plot this gridded object using this plot function, you should be able to get the gridded map of Bosnia that looks something like this. If this is true, then we can move on to the next step, which is called interpolation. So you remember that we said at the very beginning that these stations, they are irregularly spatially distributed. And then we created this grid. And then some of these grid cells are going to have stations associated with them and others won't have. So this is where we're going to be using interpolation, or in specific, an inverse distance weighting method. This is a method for estimating unknown values from a set of known points based on their distances. So this method assumes that closer points are more similar than farther ones, and then it assigns weights to the known points inversely proportional to their distances to the unknown points. So then the unknown value is calculated as a weighted average of the known values. And for that purpose, we'll be using the gstat package in R. And to work with this package, we need to have both the grids and those points in the SF format. So we already have the grid in the SF format. We simply need to now convert that WAQI df clean object. We need to convert it into an SF object. So let's do that. Let's create an object which is called WAQI SF. So this is going to be a points object converted into a simple features format. And to convert into an SF object, we simply use, as we did before, st as SF. And because we are converting points, we need to specify coordinates. So coordinates are the list here, and the first value should be this longitude value, or long, as it is called in our data frame, followed by the latitude, or lat. Now, because we are transforming a data frame object into an SF object, the SF package is not going to know what is the coordinates reference system unless we provide it. So that's what we're going to do next. We're going to provide it using this st set crs, and then simply we're going to pass here 4326. Right? I'm just going to quickly show you actually how this looks like after running and quickly just inspecting this object. As you can see, we have now this geometry field. Each of them are points as expected, but we also preserve this AQI field, which stands for the air quality index. Now that we have both objects in the SF format, we can finally call gstats, and from gstat we'll be using IDW, which is a shorthand simply for inverse distance weighting. And we're going to create an object to which we're going to apply this, which is going to be called WAQI interp, which is kind of a shorthand for interpolation. So within this one, there are several things that we want to do. First of all, we need to define our dependent variable, or what we actually want to model. So we want to model this, or we want to predict air quality index. So we provide that. And then here as a function of 1, so an intercept. The second thing what we want to provide here is the points SF object that we just created. And the final one is the grid. So basically country underscore grid. Okay, so we can actually run this. And once we actually run this, we're just going to quickly also inspect what we actually got here. So this is going to be in the data frame format. So then we're just going to go here and do the heads. I'm going to quickly just pull this terminal so that you can see what's going on. So this is actually, so it's not a DF format, it's actually an SF format, obviously, because we provided 2 SF objects to it. And we know that it's SF format because it says here that it has a geometry field. So here we got several things. Of course, we have the coordinates. Now the coordinates here are expanded. So here it shows only the first 6 features, but I can tell you this has actually a few thousand. So we successfully interpolated. The third column here, this is the predicted value, of course, for all those cells that do not have. And then finally, this is the geometry object. So this is what we have. So what we can actually do next is we don't need all of these fields, obviously. So we can just build a pipe here, and we can only select the first 3 columns. So those are, of course, the predicted, so the longitude, the latitude, and then the predicted AQI. So simply here we can say from 1 to 3. And then you probably noticed also that that predicted AQI has a really weird name. So basically it's called var1.pred. We can rename that. Again, we can use here dplyr and the function rename. So the way it works, you first of all define the name that you want. So I'm just going to quickly revert it back to AQI, and then equals to the old value. So as I said, var1.pred. Okay. And once we do that, we have then everything we need, and we can move on to defining the elements necessary for plotting. Before we jump straight into creating our first 2D map, I would like to customize a few things, and one of them is the theme. So instead of going into ggplot code right away, we can simply here define our theme for the win as a function, and then specifying different elements that we want to use. So here, instead of going for the theme void, I'm going to go for theme minimal. And the reason for that is because I also want to turn this 2D map in ggplot2 to a 3D map using rayshader, and rayshader doesn't really work well with theme void, so we're going to using theme minimal, and then we're going to specify some further things using theme. And some of them are, for example, with theme minimal, you're still going to have those access lines. So one thing I want to do here is just remove them, and to do that in the theme is to simply use this element blank. So apart from the access lines, I also want to, for example, remove here access title. So access title dot x. Also want it to be elements blank. I also want that to go for the y, and also for all the text coming from the X and Y. So I'm going to also here put axis text X, axis text Y also to be blank. So apart from these things, we can also determine the legend position, and the easiest way is simply to describe where you want it to be. And there are 4 ways to do that, of course, right, left, bottom, and top. We can put our legends on the top. There are several other things related to the legend that you can customize, and one of them is, for example, the legend title. Because legend title is text, you need to let ggplot2 know that it's a text. So here we are just saying it's element text, and then within these brackets, we can then specify something. So, for example, size in pixels, we can go for a bit lower, like 9. And for example, for the color of the text, we can choose, let's say, charcoal gray. We can do the same thing for not just the legend title, we can do the same thing also for the legend text, like this. And you can also specify other things like, for example, a plot title, subtitle, even captions, but for us, that's not really necessary at the moment. As I said, with the theme minimal, you do need to still remove some of the background lines, and one of them are also the panel grids. There are 2 panel grids, a panel grid major and panel grid minor. So we can also specify here that we want to remove them using this element blank, just like this for the panel grid major, and then just below it for the panel grid minor. There are other things that you can also specify, and one of them is how much of that blank space you're going to have around your borders. We want to shrink it as much as possible, and for that purpose, we're going to be using here plot margin. So plot margin works with units, where you actually define a list of 4 elements, each element being one side of the plot, how much you want to keep it at bay. When I say keep it at bay, I mean, if I define here top as 0, it means it's not going to expand, it's not going to shrink, so it's just going to be as is. I can also do for the right hand side, and then also the bottom hand side, and finally wrap it up with the left hand side. What is also important here is that immediately after this, because we're working with units, you also define units. I usually use lines, but you can use millimeters, centimeters, inches as well. And finally, you can also define, what is going to be the color of your plot. So plot's background itself, this one is the rectangle. So we need to tell here ggplot2 that it's element rect. And then inside of this, we, for example, want to fill it with white color. And to keep the borders of it, which is basically just the color argument, to be missing. So that's not important for us. And legend itself is a separate object in ggplot2, which means that here you also need to define legend.background as well. So those are some of the things that we can use to define our theme for the win. So the next step is to define the colors. And for this, I want a bit of stronger colors, which have some kind of a lighter version, so lighter palette or lighter value for lower values and darker colors for higher values of air pollution. So we can first of all define poles here, and we can use here the HCL colors. You can check some of these colors and the palettes they offer. In this tutorial, we're going to be going with the Viridis palettes, and we're going to first of all define 5 basic values of this Viridis. So here I just passed here that I'm going to go for Viridis, and importantly, I want to reverse here the palette, because if I go for a non-reverse, so a standard one, actually for higher values I'm going to get the light version, and then for lower values I'm going to get a dark version, which is not going to correspond with what's going on here. So that's why I'm reversing it. And then I'm going to create a new object, which is going to actually extrapolate this. For that, I'm going to be using color ramp palettes. And color ramp palettes, I just simply put here this argument calls, and then I specify how many new values I'm going to create. I can even go as high as 512. After we're done with colors, the last but not least step is to define the breaks. So I like here to go for a class int package, which offers several nice breaks. The advantage of this package is that it creates breaks based on a certain classification method, which are kind of more or less equally spaced, and they are really useful to use so that you can effectively show how your data is distributed on the map. So from class int, we can call class intervals, which is the main function from this package. And then within this one, we need to provide what is the data frame and then column that we want to use to create these breaks or bins. So in our case, it's WAQI_interp. So this is the name of the data, and then AQI is the name of the field. Then the next step is to specify the number of those. We can, for example, go for 6. And then the style is what is the method that you're going to use. I'm going to go for equal, which creates equal breaks, and this is going to be looking nice on our map. And last but not least, here you need to specify that you're going to be using breaks from this object. All right, guys, we're ready to create our 2D map of air pollution for Bosnia-Herzegovina. And because here we're dealing with a European country, I will be using a Lambert conic projection. But if you are mapping a non-European country, you can simply omit this part. Okay, so we're going to start off by creating object map, calling ggplots, and then adding our one and only layer, which is an SF object. So we need to use GMSF argument. So we need to declare the data here. So the data is WAQI underscore interp. And then because this is our main aesthetics, we need to define here AES. And we're going to be filling the colors with the AQI, but we're also going to determine the borders of this one also using this AQI. And then finally, we don't really need any size here, so we can just put that size of those borders of each of the grids or grid cells is going to be less visible. We can then go on and actually define the colors. So for that, we can use scale fill radiance. And then within this one, we can do several things. First of all, we can define the name, so or title of our legend. So it can be air quality index. Second, we can define what are the colors that we're going to be using. So for that, we can use this pal object where we extrapolated the number of those various values. Then here we can also define breaks. So our breaks are have decimal values. So what I'm going to do here, I'm going to round them. So I'm going to round them to 0. And then finally, what we can also do is also for the labels themselves, I also want to have labels that are rounded. And then finally, if there are any missing values, we can also define them. Let's say that for the missing values, we're going to use a light gray color, but I don't really expect them to happen here. Then after we define this for the filling of those cells, we can also define for the color of the border lines. So scale color gradient. And then using the guides, we can specify what actually shows in the legend, because now we have actually two aesthetics. We have fill and color. Well, we don't want color. We don't want the legend for it. So we can just say that color equals none. And then proceed with fill and define a color bar. So guides, color bar. Color bars are good for continuous data. And this is also our case. So what we can do here, we can say that the direction of our color bar is going to be, for example, horizontal. That's the first thing. Second thing, we can also define the width and the height. So for the width, I'm going to go for a bit longer one. And for the heights, because we're talking here about horizontal one, the width should be then thin. So let's say 0.5 should be fine. So bar width and bar height. Once we define that, we can move on and add the coordinate reference system. So coord underscore SF. If you didn't change this one, you don't need to add this. So if you're working with a non-European country, you're not using Lambert projection, you simply do not need to write this line. But if you're just working on this tutorial, you're trying to replicate this code, you can then include this Lambert projection here. And then finally, we define the theme for the wind. So we're just going to call it here. And that's going to be it. Now go ahead and save locally the map that we just coded using ggsave. Where we first of all can provide the name of the file that we want to save. So for example, Bosnia AQI.png. So here I'm using the PNG format, which I can also specify ggsave, but it's not necessary because it's going to pick it up from here. The second is the object that we want to save, so it's called map. The third are the dimensions. So width can be, for example, 7 and height 7. And you might be asking 7 what? Well, those are inches, which are by default here and which I like to use. But if you want to change, you can, for example, instead of inches here, put centimeters. Let's see, cm, or for example, you can use also pixels, px. So I'm going to use here inches. And finally, I'm going to declare the background of this plot to be white. So that's also something you can do and customize the way you want. So after you run this, you should be able to see a map that looks something like this. Alright guys, that's not all for today, because I would like us to turn that 2D map that we just created using ggplot2 into a 3D map using a rayshader, and this is how you do it. So from rayshader package, you call plot.gg so that you can create a scene, and the first argument that you pass to this one is the name of your ggplot2 object, which in our case is map. After that, you can specify several things. So one of them is, for example, width. So width here, again, it's in inches. So width and then height. I'm just gonna go for the default one, 7 inches. Then you can also specify what is gonna be the window size of the newly created window that's gonna create your scene. So here, what I like to do, you can pass only one value. I like to do for both the width and the height in pixels. So 800 by 800 pixels. Of course, you can change this one. Then we actually go to the part which concerns the outlook of this 3D map itself. And one of the things that we can do here is determine the height of the spikes. This one is called scale. The default scale is 150. It doesn't tell you much until actually you see in practice. But here we do have kind of more or less similar values. They're not like, huge spans between the minimum and the maximum air quality index values. So I'm going to go ahead and really exaggerate the scale here, and I'm going to increase it to 500. So you will see what we will get, but you can always readjust it here. There are other things that I want to change, and one of them is that there is some kind of a plane that rayshader creates around your map itself to give it like more kind of a 3D looks. I want to just simply kind of put that plane, which is called here solid. This is the argument that handles it. I just want to turn it off or kind of minimize it here. There are other things that we can also do here. One of them is that we definitely want to have shadows. So we want to also have light, and you can determine how strong the shadow is going to be. And there is an argument here called shadow intensity. It's not very intuitive because it ranges from 0 to 1, and 0 here is actually the strongest possible shadow, while 1 is the weakest. And I don't want shadows to be that for now, so I'm going to go and minimize them by using the value of 1. There's also one more very useful argument here, which determines what is going to be the angle of your light, and that one is called sun angle. So this is in degrees from 0 to 360 degrees. And if you're not sure how actually light is positioned, how it works, and how you can set it up in rayshader, and what are going to be the effects of your setup, you can check one of the earlier tutorials that I did where I show actually in depth, step-by-step, what that means and how it's going to affect your scene. But for this purpose, we're going to be going for 225 degrees angle, which means that the light is going to be coming from the southwest. There are other things that you can customize here. One of them is, for example, the angle of your scene. So this is controlled by 5. And here I like to go for something which resembles more like less flat map. So something closer to 90 degrees. And in this case, I'm going to go for 75 degrees. So there is still kind of an angle there. Then you can also specify the zoom. If you want to zoom in completely, that's 0. If you want to zoom out completely, that's 1. So I'm going to go for something in between, like 0.6, for example. And finally, you can also choose using theta whether your map is going to be tilted or not, or rotated around the axis. So in this case, I don't want it to be rotated, so I just go for 0. There are other things which are optional, and one of them I like to include. It's called multi-core. Which, if you set it to true, it allows you here to utilize the fact that if you have more cores. So this is basically how you define plot.gg. If you're not sure, how this actually works, and if I didn't go here in depth, I also have one more tutorial which is going to help you also understand better how we can use this plot.gg from rayshader to turn 2D maps into 3D maps. The next thing is to check the scene, and once you actually run this, a new window will pop up with the scene, and the scene should look something like this if everything went well. So if you're happy with the scene, I am actually happy, because here you can clearly see that we added this 3D effect. We can now go ahead and actually render this scene and save it locally as a high quality image. Okay, let's render our scene using again a rayshader, and its arguments called a render high quality, which will allow you to render the scene as a very high quality image on your local drive. The first thing we need to define here is the file name. So I'm going to go ahead and use, again, something like Bosnia AQI, and then just add here 3D so that I don't overwrite the other file. And also you need to specify here your file extension, and I like to go with the PNG extension. There are other things that you can specify, which is more or less about, they're optional. So one of them, for example, is there's going to be a new window opening up, which can actually show you how the rendering goes, what is the process. So I like to turn this on, and for that you can use preview equals true. There's another option that you can, as it renders, move the scene, but this can lead to disastrous consequences, and one of them being that just like your whole session shuts off. So I like to turn this one off using interactive equals false. Of course, there is an option here whether you want to use a light in the scene or not. So you can specify using light equals 2, and we will of course use lights, so light equals true. And then there are several things that you can specify about light. So I go into more in depth about setting the light in this rendering part of rayshader in one of the previous tutorials, so check them out for more detail. Here I'm just going to go quickly through it since it's not the main focus. And one thing that you can do here is the light direction. So this is where the light will come from when you render it. So you remember that we put sun angle to be 225 degrees, which is something like southwest, and we're going to go ahead and do it also here so that we want a rendered image to have the same as the scene. There are other things that you can also specify here, and one of them is the light intensity. So that light source, how strong it's going to be. Here, the default one is 500. It's not very intuitive until actually you see what's going on. But one thing I can tell you from my experience that 500 is very low. So we're going to actually double this or even more. So I'm going to put to approximately 1000, say 250. And the third parameter about light is light altitude. So light altitude is basically, it's simply, okay, what is the angle of your source of light? And as you can know, there are different angles, and the shorter or the smaller the angle, it means that the light is going to cast, it's also smaller. So here we're going to go for the maximum light altitude, which is 90 degrees. What this will also allow for not only that the light is going to be very strong, but also the shadow will be minimal, since our source is going to be basically casting the light from the top. The last few things are the size, and also whether you want to run this in parallel using, again, your computational resources. So I do like to set parallel equals to true. And again, I can also specify here width and height. And here I go for pixels, which are the default unit. So I go here for, let's say, 4000 width by 4000 height pixels. Of course, you can decrease or increase this as you see fit. And here it is, the final 3D map of air quality index for Bosnia and Herzegovina, and you can clearly see here a variation, and those values that are higher, they are extruded upwards, and those that are lower, they're extruded downwards. And that's all for today, folks. In today's tutorial, you learned how to create pretty and effective air quality index maps, both 2D and 3D. But most importantly, you learn how to communicate with the World Air Quality Index API, then how to download the data directly through R, and then how to interpolate data points to create these amazing 2D and 3D maps or air quality index. In today's tutorial, we created one such map for Bosnia and Herzegovina, but I'm really looking forward to seeing your own use cases and how you take this tutorial on a journey across the world. If, however, you are interested in replicating today's analysis, I've prepared a GitHub repo in the description below. Feel free to clone it, reuse it, modify it as you see fit. If you have any questions, comments, or just feedback, you can reach out to me here on YouTube, but also on X and Instagram. If you're new to R and you seek to expand your data visualization and geospatial knowledge with R, I prepared a few cool tutorials for you, so do check them out. See you next time.